Well, it's my pleasure to introduce Bingyu Zhang from Center for Quantum Mathematics, and he's going to tell us about circle action of microlocal kernels. So take it away.
Okay, but okay. So, could you give me a co-host to my iPad?
Okay,
I think it's co-host now.
co-host.
Ah, okay.
You're both co-hosts, actually.
Okay, but still that cannot work. Okay, anyway, I plan to write something, but it seems that the node action doesn't work. Okay, anyway. Okay. So let's start. Okay, thanks for the invitation and thanks for introduction. Actually, it's my first time to go talk here. Okay, today I'd like to talk about circle action on microlocal kernels. Okay, let's start. Basically, my motivation is a contact non-sequential theory, and here let me denote the B hat to be the frequentist wall, and A equal to pi square is the error. And the contact non-sequential theory problem is that if we have a contact embedding between two frequentist wall, and what do we have? The first result is that if we by the Ashburn-King postulates that if there's an integral, positive integral between two errors, then we'll have the Euler error bound. And then later, this restriction is removed by Chiu and Foster using different methods. And today, I will mainly focus on the Chiu's proof and basis using microlocal sheaf. And the idea is that Chiu construct another kind of closed string invariant like symplectic mod or contact homology using microlocal sheaf, and specifically for array open set here. For array open set here, we can construct the mod L equivariant invariants or based on using a sheaf over actually here is the mistake that so x squared times r squared. It's a mistake. And the key feature of the series that is cohomology is a module over the classified space, cohomology ring of the classified space. And we can also define a fundamental class of this open set in degree 0. And then what Chiu proves that
can you say again in the previous slide? So the sheaf is over what? It was over R2D plus 2, or it was
it says x squared, since actually here I consider code and bound over x, and then here the sheaf is over x squared times r squared.
X squared times r squared.
Yeah.
And also is, maybe you said this, but the Z mod L action, is that just the roots of unity on the circle?
No, this action is algebraic. Maybe I will explain later.
Okay, no problem.
And now basically, let me just introduce how to prove that. And what Chiu proves that in case that there's odd prime and is greater than 1, and then Chiu compute this invariant for frequentist ball as a module over the cohomology ring. And in particular, as a odd prime, we know that the cohomology ring over finite field is a polynomial ring over u and theta, well, u degree 2, theta degree 1, and theta squared to 0. And then we can prove that the fundamental class admit a decomposition in this way, and also the fundamental class is non-zero. Now, suppose we have a contact embedding. Now we can construct a model morphism of a degree 0. And this model morphism preserves the fundamental class. In this way, we can obtain two decomposition of the fundamental class of B little a hat. The first decomposition comes from our theorem here, and it means that it's non-zero. The second decomposition comes from a decomposition of a bigger of a B capital A cap. And now, if we assume the small a is bigger than capital A, then the degree reason will imply that the decomposition, the image of a lambda capital A is 0 for LE big enough. And then the middle term will become 0, but the right term is non-zero. Then we got a contradiction. Okay. The point is that we use a trick that if I is the approximation of L is big enough, then we got some numerical consequence. For example, is smaller than capital A. And then this is kind of a numerical approximation that I call the numerical approximation. And in my previous work, I construct some capacity using this idea. But the question is that, of course, okay, we find some numerical way to realize S1, but in computation, we find some real S1 symmetry. So our question is how to construct this S1 symmetry. And this is the topic today. And okay, the talk is based on some. Okay, here I mean a working preparation means that you can find most of the results in my thesis, but I still need to write some article. Okay, let's start from something very beginning. Now we fix the smooth manifold X and the coefficient ring. And the point that sometimes it could be that. And let dx to be the direct category where shifts over K modulo. And today I won't talk about anything about coherent size, so it makes sense to just use dx. And then the most frequent stuff we will use is the locally constant shift supported on some locally constant set. And in this case, we usually just write this shift by the corresponding locally constant set. For example, for open set, we just write an open set. And for a closed set, we just write a closed set. And it's characterized by the stock over a point in this locally constant set that is a given modulo and otherwise 0. And main notation we need is a microsupport. It's a notion of microsupport. And for given shift over X, and we define the microsupport to be a closed subset of a cotangent bundle. And measure some non-propagating direction of F. It means that, okay, what's the meaning of a non-propagating direction? It means that if we consider local section of F near a point Q, and we consider direction, a co-direction at Q, let's say P, then we can consider the restriction of this local section over U and to U intersect with F smaller than 0. And then we say F is propagate here if the restriction map is isomorphous, and if it is not, we call it non-propagating. And then we can use some 6 operation machine to formulate this limit by say 6 operate by in the left hand side. And then we formulate the definition as a ball. Okay, for example, if we consider constant shift supported on an open set, the microsupport is given by the section inside the ball, and at the boundary of the set, the microsupport is given by exterior conormal. And for some manifold, it's given by the whole conormal. And for closed set, it's given by interior conormal. And in general, we can find that, and actually we can prove that the microsupport of F is Lagrangian if and only if the shift F is constructible in some sense. And here, for constructible, I mean we have many pieces of constant shift, and they are combining by some non-trivial extension classes between different pieces. And okay, crucial feature is that the microspore is conic in the sense it's invariant on the dilation. Okay, let's go back to the definition. If we replace this b by a positive multiple of b, you'll find the first condition we just replace f by lambda f, and then the second condition will not change since it is given by an inequality, and then you times a positive multiple will not change the inequality, and then we got a result that the microspore is invariant on the dilation. And so, but to resolve this problem, we introduce an actual factor RT, and we consider shifts over x times RT, and we identify the cotangent model of x times RT by in this way, and R tau is given by the dual vector of RT. And then we introduce the sectional microspore of f. It means that it means that we first project the factor here to its infinite boundary, and this infinite boundary is a contact to morphism one jet, and then we project it to the cotangent boundary. And actually, we can also just project to one jet to got something, to got some Lagrangian. Okay. Okay. Now let me see some example here first. First, let me just look at the picture here. On the left hand side, you can see that this locally constant set you can think it as it's a interior of some of the from bounded by the from projection of a Lagrangian R naught in J1 R, and then the one shift condensation, one shift was given. If we consider this shift, we using our previous computation as a boundary, you can find that the single spot is it's a simplification of this Lagrangian R naught. It's a Lagrangian somehow it's a Lagrangian R naught, and by some technical reason, we hope to obtain some shift with non-negative microspore. The first thing is that we to define the second microspore, we consider the positive tau invariant, and that's the first reason. And the second reason, we hope that the shift is propagated along a given direction. And then using the idea of Chiu-Tamarkin, we consider the left orthogonal complement of shift microspore in negative direction, and so in this way we mimic to some shift that is microspore in a positive direction. Here I mean positive is strictly positive, and then one can show that in this case, if we have an object in the Chiu-Tamarkin category, even though we cannot prove this is strictly positive, but at least it's non-negative. And the right-hand side is an example of a Chiu-Tamarkin category, which is constructible. We have two pieces, 1k and 1k minus 1. And here, I mean, we have a non-trivial extension between this class. Okay, now let's consider the rib flow of the standard contact form on one jet space. Since we are considering sheaf, we first consider the translation on the base. It's very simple by this formula. It's given by here. And on the category sheaf, we consider direct purple this purple image, direct image, and one can prove that by some microspore estimate to show that on this TC star plays the role of a rib flow on the contact form, the standard contact form on one jet space. For example, here, if we have a let's still consider the sheaf corresponds to the Lagrangian R naught, we can see that we can push it along the t direction, and we can construct a morphism tau CF for a sheaf with non-negative macrosport, such that it's from F to its from F to its translation by T. In this example, oh, I don't have a now I don't have a. Let me try. No, okay, I cannot write something, but anyway, in this picture, we can find that we can prove that this tau-c is a generator of H0 here at this intersection of two pieces. And in this way, you can find that if the translation tau-c TCF is if we translate smaller than L, then tau-c is non-zero. If you translate by a dozen bigger than L, then the tau-c is 0. And then if we define the minima, say such that the tau-c is 0, and then we will find some numerical invariant. And here we call it the shift energy. And in this example, we will find that shift energy equal to L, which is the length of this ripcord. And actually, we have some more sophisticated numerical invariant in the work of Asano and Eek. And now I want to explain them now. Okay, last let me introduce a notation called shift convolution, which is a variant of a Euro shift composition, which is more often appear in the theory of algebraic geometry and called the Frey-Mukai theory. And here, let me say that if we have a projection, we have a product bundle, and now we denote the projection by pi, and the lower subscript to denote the fiber of the projection. It's like some integral. And if it's a vector space, and we define the summation map by Sn. Here n means that we have n copy. And now, if we take two shifts, one over x1, x2, T1, and the second one over x2, x3, T2, and then we first we define the convolution to be the shift over x1, x3, and T1 plus T2. And we also introduce some formal integral notation to make it more familiar with. The first thing is that we just product them to the biggest space, x1, x2, x3 times R1, R2. And then we integral, which means put forward along x2. And second, and next we take a sum with respect to 2t. And that okay, you can see that from the formal integral notation that why we call it a convolution, since it is literally a convolution. Now let's go to our central topics, microlocal kernel. Okay, maybe first I need to mark something. Okay, now we can prove that for proper base change formula that this category equipped with a convolution functor from a symmetric monoid category. It means that we can do some kernel calculation in the Euro way. And second is that we can define a convolution functor using this using a kernel. And this way we define a monoid functor, which means that the category kernel acts on category dx similar. And Tamarkin proves that the object, the identity function of a Tamarkin is represented by the kernel, the kernel that is a constant shape supported on diagonal and times on half interval. And so in this way, but here we in the Tamarkin kernel we access from the left, and in the above we access the kernel from the right. And so in this way we can see that the kernel, if we, in general, if we have a general kernel, the kernel descend to a convolution functor on the Chiu-Tamarkin category. Here I just choose the action way to make the action is compatible, one from left and one from right. And now, if we take some open set in the coterm bundle, and we take its supplement complement to be Z, and then we consider two categories here. One is given by sheaf microsphere in Z, and one is left orthogonal complement. So we first study. We will have an inclusion of two triangular subcategories, and we hope to consider a projector into these categories. And we call this functors microlocal projector. And if in general, if for some open set U, the two projectors are represented by some convolution functors with two kernels BQ and QU, we call this open set is admissible. And actually, we have extra data is a distinguished triangle. And in this way, you can see that it just means the two kernel BU and QU form a decomposition of a diagonal of the identity functor. Okay, now let's see some example first. If we just consider the whole coterm bundle, and in this way the Z is empty, and it means that okay, if a section of microsupport is empty, it means that the zero microsupport is seen called non-positively. And then if I have a sheaf in the Chiu-Tamarkin category, but it's also microsupport in tau non-positively, then since you can think the form as a inner product of a sheaves, and so if it's something is inside itself and it's not orthogonal complement, then the sheaf is zero. And in this way, we say that DZ is the empty side is a zero sheaf, and and then another pair of another kernel Q is zero, and with P is nothing but the identity functor. Okay, seems that is okay. Well, no question. Okay, and actually, we can prove that many sets are admissible. For example, bounded open sets, Toric domains, and unit this bundle. And the first proof is given by Chiu for Bohr, but later I realized his method is generalized straightforward without any modification to the rest case. Okay, maybe the next case is a more complicated one, but it's a good geometric example here. Is that for complete Riemannian manifold and the distant function is D, and then we can find that the microlocal kernel of this open disk bundle is going out. Okay, here's a very long formula. Okay, actually the formula is not quite important. It's important since that it is some kind of a discrete Moore loop space of X. Okay, we can do some approximation like Euro, and then we have the first consequences that if QQ prime PP prime is a sectional microsupport of this kernel, then there is a geodesic between Q and Q prime, such that its initial spin is P. And in general, we can prove that for bounded open set has restricted contact boundary. And then the similar result holds that if QQ prime PP prime in the sectional microsupport, there's a rip code of a boundary from QP to Q prime P prime. So in this way, we can think the microlocal kernel as some version of condensation of a rip flow of the boundary. Okay.
So can you just explain? So that the last thing you said was supposed to be a consequence. So how do you go from a discrete? You're going from a discrete geodesic to an actual geodesic, or?
Sorry.
So you said that in the proposition you're computing this kernel to be like this discrete space. Can you just explain what? So and then how do you conclude that there exists a geodesic from that?
Well, actually, we need some computation.
I see.
But point that, okay. If you start the boundary of this set, it means that you. Okay, for first, we can compute the microsphere of this constitution supported on the discrete loop space. And it's given by the boundary of this set. And in particular, it means that we got something, some equality taken equal here. It means that we have a sequence of point here is Q0. From Q0 to Qn, such that distance of between every pair from Qi to Qi plus 1 is given by it's smaller than it's equal to d divided by n. And if we take a good remainder metric, you will find that and restrict the we will restrict the remainder metric to make sure the injective radius is big enough, and then we can connect it to got a discrete piecewise geodesic from Q0 to Qn. And next we take integral along Q1 to Qn minus 1. It means that we can choose the middle term between Q0 to Qn. So in some case, in some sense, we can take a good approximation of geodesic. Okay.
Okay. Yeah. Thank you.
Okay. Okay. Well, okay. And I would like to tell you the central property I need is that since PU is a projector, it means that the functor square, since functor itself is idempotent, and then the kernel as some kind of a matrix of the kernel. We can also prove the kernel itself is also idempotent in this way. And secondly, we can say the home in this way. And so, well, okay, that creates everything to us. Okay, now to be simple, let me start from the non-current theory. Okay, now we start from the kernel PU, and we want to construct a sheaf over R. And how we do that? We pull back along the diagonal of the x direction, and then now in this step we got a sheaf over x times R. And then we pull forward along x to integrate something. And by previous microsphere estimates that the microsphere of a PU is given by some ripcord. So if we pull back by diagonal, it means that this ripcord is closed. It means that we got some rip orbit, and then the dark image means that we just take the integral along some space of loops, and then we call this shift by f1. And the definition of S1 is nothing but we would take a stock and then take a dual. It's simple, but geometrically we will see that the stock at T means that we get an action bar of a ripcord. For example, for the kernel of a whole coordinate bundle, the F1 is nothing but compact polynomial homology of X. And it means that actually it means that we can only collect constant loop inside X. Since you can, if you think the coordinate bundle as a disk bundle of infinite radius, and it means and then for then in as a disk bound case, you will see that you will get some geodesic of infinitesimal length. It means that it's constant. And now, if we use adjunction formula, and we can formulate everything in this form. And then, if X is orientable, we can rewrite in some different way as a constant shift supported on the diagonal. And then, like the first we got the first isomorphics in this two way, and second we use obtain the isomorphisms in by the previous slides here. And then the point is that it means that when X is orientable, the non-equivariant Chiu-Tamarkin complex just as the endomorphism of PU. As if we think the Tamarkin category as a triangulated persistent category. And in this case, we see that in the non-equivariant Chiu-Tamarkin complex, we have a natural unit product. And this unit product is greatly commutative. The first example is as usual for the whole codon bundle, we will get the Euro cup product. And second example is that for disk bundle, we can prove that using our previous formula that it is isomorphic to the homology of here is a homology, but not cohomology. There's a typo here. It's isomorphic homology of a free loop space of a given length. And in this case, we can prove that the unit product is the Chassarin product. So this is kind of a obtainable isomorphism. Now, the point that let's start now we can start our main construction. The point that we start from our idempotent identity, PU is isomorphic to PU convolution with itself of L tabs. And then we plug it into this functor here, this functor, and then we use idempotent identity first. And next we expressed in the second line, in the second part, in the right hand side, and we call the right hand side as FL. And then this is given by external product of PU. And then we product by a twisted diagonal, and then make some integral. And this twisted diagonal is given by a formula here, and it means that we will see that the maxpole of a PU box with itself is just several copy of the rib form, and so it is again means that we obtain some kind of a rib floor, but in discrete way. And the point that here, this FL, since we have a several copy, external copy of a PU, and then we can lift it to a Z mod L equivariant drag category. That's okay. And then the original, this is the original definition of true. It means nothing. We just enhance the Z mod L symmetry with the non-equivalent one in this way. And okay, and now I can explain that the mod L symmetry. It actually means that so algebraically it means that we just take a singular permutation of the kernel, and geometrically, actually we mean that we take if we take one given rib chord, then we consider is gamma folding a gamma covering. It's given by if we have a rib chord of a gamma t, and then in FL the corresponding rib chord is gamma LT, and then we use a L curve of S1 to obtain this Z mod L action geometric. Okay. Okay, now let's see some examples. For example, again, for the whole codon bundle. Okay, non-equivariantly, the sheaf FL is still gives us the same cohomology, but now we consider the group action for X. Here we identify X with a diagonal here, and then the group action is trivial. So the cohomology is nothing but the Euro cohomology tensor with a ring here. And similarly, our Viterbo isomorphism is still true for all equivariant variant. Now we can now we go into the construction of S1 structure. Let's go back to the Hausdorff chain. We start from associative algebra, and we consider the Hausdorff chain compact as a simplicial abelian group. It means that we have some different tensor product, and we have some boundary and degeneracy map given by product and the unit. And then if we actually given cyclic permutation with different factors, we got a cyclic abelian group. Now, what's interesting to us is that as we have an independent identity for kernel, so actually we can prove the isomorphism, independent isomorphism, through that P is actually a bind algebra in this monoid category. It's similar to the associative algebra case that we have a bind algebra, and even though we don't have we have a co-unit here, but eventually we can verify some compatibility condition of a Fisher map and the degeneracy map using this bind algebra structure. And then in this way, we collect every copy of a self-convolution. We got a simplicial object in the Dirac category. And Fisher map and degeneracy map just come from the important identity. And then as a previous slide here, using this recipe, we apply this function first, and then we can take in account the cyclic permutation of an external tensor producer, where we got as a cyclic object in the Dirac category of vector spaces or K model. Okay, now so far it seems that the story is perfect, but the problem is that what we got is actually a cyclic object valued in the Dirac category, and it is not a cyclic complex. Since actually we need to, it is non-trivial to lift the degeneracy map to composite level. And since now we mod very many homotopies, so it's very hard to lifting this degeneracy map very in some homotopy coherent way. So maybe in some setup we can run this machine in infinite category, but now I choose a more classical solution that we take some resolution. The first thing is that the first idea is that it's hard to lift in the degeneracy map. Then we forget them. So we will got a pre-cyclic complex. It's like when we consider non-unital Hausdorff complex. In that way, and the second thing is that it's more or less a technical problem that instead of consider the resolution of a PU, we need to consider the resolution of a QU, which is I recall that we have a parallel kernel PU and QU. And actually, PU is used to define some whole Chiu-Tamarkin complex, like whole symplectic homology, and QU is used to define some positive Chiu-Tamarkin complex, like the positive symplectic homology. It means that we remove some constant loops. And now we can prove that if the coefficient ring is a field, and we take resolution of QU, and then if we define this pre-cyclic chain complex on chain level, then we will got a pre-cyclic chain complex that denoted by that represents the positive, some positive theory. And now the next things are more or less some routine things that if we consider a mixed complex Dg algebra over this it's a Dg model over this Dg algebra, and then it is a one model for algebraic SY actions. And then we also have the Londy-Seagon construction that is a functor maps cyclic complex, pre-cyclic comes to mixed complex. Now, as we already have a pre-cyclic complex, and then we got a mixed complex in this way. Here maybe I think I should send to share that your paper helps a lot on algebraic part of a mixed complex and some.
Sorry, can I ask a question? Yeah, I was just wondering. Sorry, can you just repeat why you used QU? QU was just to get the positive symplectic cohomology. Can you do everything with PU as well? I didn't quite understand that.
Yes, I can.
You can. Okay.
Yes, I can. Yes, I can.
Thanks.
And actually, the process step is that first we in this case we first define the positive theory, and the next thing is that in this case we even though we cannot define the full theory for general U, but we can define it for whole cotangent bundle, and then we have a natural morphism for Fs1 cotangent bundle to F plus U, and then we take a co-kernel to obtain the full theory. This is a definition, but in practice, we can find the full theory directly. But now I didn't mention this part, but that is a real procedure I did. Okay. Now in this way, we okay, after the procedure I described before, that we obtain the full theory of Fs1, and then we define the S1 equivalent Chiu-Tamarkin complex as follows. And okay, and then as a direct consequence of the definition, we will have a JSON sequence in this way, and the point that okay. It actually it's routine to obtain the JSON sequence for mixed complex, but the point is that we need to prove the third term is a non-equivalent one, but we can't do that. Okay, and so we have a JSON sequence here, and now as usual we still consider the whole cotangent bundle case. We show that we show that the complex as a complex is nothing. It still got a complex exploded cohomology, and the trio SY action give us a zero con operator, and then we got this computation. Now let me tell you some property. Yes, it is at zero, but it's not hard. It's just long. The first thing is that it's modular over classified space. And second thing is that we have a restriction map. And third thing is that we have a natural invariance for compactly supported Hamiltonian. Okay, and then now let me give a short time to discuss a little geometric application. Is that now if we assume X is orientable, and then we got the Euro fundamental class in H0 of the cotangent bundle, and then we use a restriction map to map it to the H0 of H0 of CTU, and then we define the fundamental class of U to be the image of this restriction map. Now we can define capacity using this fundamental class and some invariance and the restriction map. The first thing is that okay, this extension algebra over S1 is nothing but the homology over simply infinity, and it is a polynomial ring. And then at zero, we define a capacity Ck to be infinity, such that the fundamental class could be decomposed by u to k times some element. It's as zero as almost every S1 equivalent theory. And then in general, we approximate in general open set by admissible set. And the theory set is a functor. All of these functions define a sequence of symplectic capacity. And for combinatorial domain, we can compute it to say that it is equal to the Gould-Hutchins capacity for combinatorial domain, and then also equal to Eckert-Hoffer capacity. Okay, and for this capacity, the first consequence we can obtain that is some kind of a explanation that if we consider the forgetful map, and for S1 equivalent variant to non-coherent variant, and one can verify that the S1 equivalent for fundamental class is mapped to the non-coherent fundamental class, and after some identification, we can verify the fundamental class equal to the tau t of PU, just given by our very long early slides here. It's given by this morphism given just using translation. And then the point is that by the JSON sequence, we show that C1 is nothing but this translation shift energy. So in this way, this S1 equivalent capacity is nothing but some S1 equivalent lifting of a shift energy. Okay, and
sorry, can I ask something on the previous, I guess 2 slides back? This so this theorem, is this by the fact that these capacities agree with the Gould-Hutchins capacities? Is this by computation, or does this follow
by computation? By computation.
I see. And have you also computed the left-hand side for within the ZP equivariant version instead of the S1 equivariant version?
Yeah, it's also the Gould-Hutchins one.
I see. So do the ZP equivariant ones contain the same information as the S1 equivariant ones, or is there some sense in which?
Well, I will explain in the last slide.
Okay.
Okay. I mean here. The more K correct variant. Okay. Now let me just start from the second one. Yeah, actually, I need to tell you, I don't know if these are equal. Actually, the point is that I have a proof. Actually, I have a proof, but I don't have ingredients in my proof. So I need a answer over that, but I don't have. And okay. And now I need to make some advertisement for the mod L equivalent variant. Is that this variant using numerical approximation trick. It is long in the definition, but the advantage is that this trick can be used for our definition for contact capacity on pre-quantized codon model. Okay, still I need to mention that I don't know if they are equal, but this is true for all known example like convex DOM and for example this bundle.
And can you say the sentence S1 theory cannot be defined in the contact case? Can you say like 1 or 2 sentences about why that's the case?
Actually, we can prove that. The symplectic variant is isomorphic to its corresponding contact variant of a pre-quantized U. You can prove such an isomorphism, and this is true for T equal to n times L. And then again, we use And then actually we at the very beginning, we have at the very beginning to define a capacity, we need the action of polynomial ring, and we need a fundamental class, and then the rest of the things is invariance. But all of them, we have all of them for contact case. But the point that maybe another point that we don't have a S1 we don't have a S1 theory in contact case, and I mean we can prove that it's impossible to construct such an S1 theory. Okay, I think maybe I should stop here. 15 minutes.
Okay, so yeah, thank you very much. Let's thank Bingyu.
Thank you.
Questions?
I was wondering, can you clarify again which part you mentioned the S1 theory over the integers? Can you clarify again which part requires working rationally so far?
Okay. Which part is here? So actually, since it's a point that since we use some classical trick to taking injective resolution, the point that we need actually we take the injective resolution of a Q, and then we need to prove the exterior product of a Q itself is still injective, and in that case I need flat. Some actually not necessary. Actually, we just need the flat one. But so in general, in some cases we can take some over that theory, but in general, to define a whole theory, I just need to assume it to be a field.
Okay, thanks.
So it seemed like in the beginning you were alluding to like some computations or applications, or maybe you could.
Yeah, okay. Yes,
Yeah,
in later slides, I don't want to discuss the previously. Okay.
If you could just say a couple of words.
Yeah, okay. Okay, we can say something about target domain. The point that okay, maybe let's get the definition of target domain here, and we take the omega circle to be some dual, and omega t circle to be some section of the dual. And here we have, for example, ellipsoid and its dual, and here it's okay. Here is project, and here is ellipsoid. And the point that we have a very concrete formula for Hamiltonian rotation, and then that's how we prove target domains are admissible to us. And then using this construction, we can prove that we can compute it as one by some very explicit form. Here it means that we have a blue sheaf called epsilon, and we have a red sheaf bar. And then once that we understood, we can understand this sheaf epsilon very clearly. It is a constructor sheaf supported on different blocks, and with it computes the cohomology of a vector space, and we know very concretely about the action itself, and then in this way we can. Okay, and the second thing is that when X omega is convex, the Fourier transform, we can compute the Fourier transform in a very simple way, and then we can show that for convex target domain, the fs1 is nothing but the cohomology of epsilon over the dual, like this, and then we can give a very specific structural theory for S1 theory CS1 of a convex Fourier domain. The first thing is that we know how to decompose how to decompose the fundamental class, and then second we know the minimal common degree, and then combine 1 and 2, we can show that well we have this result here. And then maybe another result, another computational result is the Viterbo isomorphism, but I divided into pieces before.
I see. Thank you. So, are there any other questions for Bingyu? Okay. So, yeah, thank you very much. Thanks again.
Thank you.